It is 10 a.m. on the dot, so we will get started with today's field trip. Welcome to the Dallas Environmental Education Center. We are located just southeast of Dallas in Seagoville, Texas. And a special welcome to the Thomas L. Marsalis Elementary STEAM Academy. Thank you for registering for this field trip and for joining us today. If you have not registered for this field trip yet, but you are watching it, you can still register by going to www.tiny.cc/EEC register, and you can still get yourself registered for this field trip. Today's field trip is going to be about physical properties of matter. And during this virtual field trip, students will discover that matter has measurable physical properties, and those properties determine how matter is classified, changed, and used. Some of the physical properties we're going to explore today are temperature. We're going to classify matter as solid, liquid, or gas. We're going to see if matter sinks or floats in water. And we'll see if matter is attracted to a magnet or not. And while we do that, we're going to use some science tools. The tools that we're going to use today are a thermometer, a beaker, a pan balance, a triple beam balance, and a magnet. Now, while you're watching our investigations, if you have any questions, you can ask those by going to www.tiny.cc/EEC-question-answer, and you can ask us any question you like, and you can ask as many questions as you like, and we will do our best to answer all of them during today's field trip. So, without further ado, I'm going to stop sharing my screen here and let the first teacher take us through the property of magnetism. Take it away, Mr. Monroe.
Good morning, students. Before we really get started into using a magnet, there's some things I'd like to remind you of. First of all, I want you to remember that matter is anything that takes up space. Also, when we're talking about the properties like Mr. Broughton has mentioned, there are several things that we are looking for. In fact, talking about properties, it's what an object looks like, how it feels, and how it acts. And so basically our focus today is using a magnet to test certain other amounts of matter, different matter, to see how it reacts to a magnet, okay? Now, talking about a magnet, magnets, they are an object that can pull things. Now, they don't pull all things. They're not attracted to all things. And just to let you know, there's a history about magnets. In fact, they're used commonly in our everyday lives, and nobody has really came out with who actually discovered the magnet. There's a lot of folk stories or folk tales that talk about a young shepherd boy that was in the mountains in Turkey, and he had an experience with the nails in his sandals. But that's just a folk tale. You know, magnets are actually a form of a very special rock called a magnetite. That magnetite, the most common magnetite that is magnetic, is something called lodestone. Now, this lodestone is a natural magnet. Of course, the magnets that we're familiar with, they come in different forms also. The most common forms of magnets that we see are the horseshoe magnet, the bar magnet, and the ring magnet. Those are the most common that we know about, okay? Now, one thing that all these magnets that I just showed you have in common, they have two poles. For example, the bar magnet, if we look at it closely, and you all probably can't see this, but at this end, there's an S. At this end, there's an N. Actually, that stands for North Pole, South Pole. So the ends of the magnets are called poles. That's where the strongest pull is located, the strongest force. Of course, on a horseshoe magnet, they are across from each other. There's an S here and an N right here. And of course, the ring magnet, one side represents the S, the other side would be the N, North and South Pole. Now, I know you guys have heard about the North and South Pole somewhere before, haven't you? Well, guess what? Our planet The planet Earth has a north and south pole. Of course, the North Pole is located at the top of our planet. The South Pole is at the bottom of our planet. So basically what we're saying is the planet Earth is just a great big magnet. It has a force field, just like these magnets have. You know, like poles repel each other. Unlike poles, they attract each other. For example, I have a couple of small bar magnets, and you can't really see these N and S's on there, but this is an N, this is an S. I've got the other one, and when I tried to put the two N's together, they will not go together. They're repelling each other. I can't force them. They're going to push away from each other. But I change it around, and I take the South Pole, and I come to the North Pole. Look what happens. They are attracted to each other. Okay? I want you to remember that. Now, our test today, we're going to be testing certain pieces of matter in response to whether they are magnetized to the magnet or not. So I'm going to start out by putting some paper clips in this dish. Some staples, a paper clip, a screw, and a very special paper clip that has paint on it or it's colored. And I'm going to take one of these bar magnets, which is very strong, and see if it will attract those. And it does, doesn't it? It pulls them. So what that's telling us is that these items or these objects that are attracted to this magnet, evidently they have some iron in their makeup. Now, I know that that screw is probably a steel screw. What people don't realize is that iron is used in the making of the metal called steel. Okay, so that's why the screw was attracted, because it does have a little bit of iron in it, even though it is a steel screw. Now I'm going to put some other objects in there, some different types of matter. A penny, another piece of metal called lead, and we know that pennies are made out of copper. And then I've got a plastic paper clip, and then I've got a brad that looks a little bit different. It's got a goldish color. I don't think that's real gold, do you? Well, let's see. It picked up the brad, but it left all the other items. So what does that tell us? The copper doesn't have iron in it. The lead doesn't have iron in it. And surely the plastic doesn't have any iron in it. But what it does tell us about this brad, even though it's goldish in color, probably has a little bit of iron in it, right? You know, magnets, they're used for a variety of different things. I can remember growing up, there used to be a salvage yard close to my house. And boy, I'd see a huge magnet on a big chain on a crane that was used to pick up scraps of metal. They were recycling metal. And today, I really think that they were using that magnet, that huge magnet, to separate the different metals that had come into that scrap yard. You see, old stoves, old refrigerators, old wrecked cars, they're made up of a lot of different metals. And so that's one use for magnets. Another use for magnets is the fact that if you ever get lost and you are forced to use something to help you find your direction, you guys know what I'm talking about. I'm talking about a compass. The needle that is in that compass is magnetic. In fact, this compass that I'm holding right here, and I'm in my classroom right now, and I know the direction north from my classroom. This compass is right on time or right on the dot because it's showing me that north is that direction and south would be that direction. That's because the needle of this compass is magnetic and is drawn to the magnetic north, the direction magnetic north. Now, I'm going to show you a little trick, just enough time to show you a homemade compass that I made by simply taking a bar magnet and tying it onto a ruler and extending it out into space. And I'm going to spin this around and we're going to see if this works. Let's stop it from swinging so much. And we're going to see if it's going to go to the north. Whoop, it's spinning. I don't know. I bet it spins back the other way. There it goes. It's going to go back the other way. There it goes. It's working. It's working, guys. There it goes. Actually, I'm going to cut it a little short because I know where it's going to end up, but I have something else that I want to show you. North is that direction, and it's almost there. Okay, so it does work. Remember when I was talking about poles repelling each other? I want you to remember that. I'm going to do something with this ring magnet. This is a little shaft that I have some other ring magnets. Of course, they're attracted to each other, right? I'm going to put this ring magnet on here. Look at that. Now, I've really messed up the compass by putting this other magnet up here close. But why is that doing that, guys? Why won't that go down? Could it be that maybe this is the south pole of this ring magnet and this is the south pole of this ring magnet? So what are they doing? They're repelling each other. If I turn it and reverse it, look what happens. It goes down. So again, like poles repel each other. Unlike poles, what do? They attract each other. Hopefully what I've done for you today has helped you learn a little bit about magnetism, and how magnets can be used to determine the magnetism of certain other types of matter. And want you guys to have a good rest of the day and a good weekend this weekend. And we'll be ready to get back started the next time you come on a virtual field trip. And at this time, I'm going to turn it back over to Mr. Broughton so he can answer any questions that you might have. You got it, Mr. Broughton.
All right, thank you, Mr. Monroe. We did have one question come in, which is, how are magnets used in real life? And magnets are used all kinds of different ways. You can use a magnet to hold a picture to your refrigerator door at home. But one way I'll discuss quickly is how cities use magnets, and they use them to recycle. So a lot of times people will recycle metal, and they throw all kinds of metal in a pile. Some metal is made out of aluminum. Some metal is made out of tin. Some metal is made out of iron. And the city can use a magnet to pick up all the metal that's made out of iron and separate it quickly and easily from the metals that are made out of other things like tin and aluminum. So cities use magnets to recycle their metal. All right, we're going to move on to Mrs. Fuller, who's going to share the next physical property with us.
Good morning, third grade. Welcome to the Environmental Education Center. We're covering TEKS 3.5, matter and energy, and that we're talking about the physical properties of matter. The physical property of matter we're going to cover in this segment is temperature. Temperature is how hot or how cold something is. This may be a very familiar measurement of temperature. This is a thermometer. It's a classroom thermometer. They're in lots of classrooms across the school district. And if you'll notice, in the middle is a long glass tube with some red liquid. The red liquid is alcohol, and on either side are a series of numbers which form a scale. The scale on this side are degrees Celsius, on this side degrees Fahrenheit. The modern thermometer that we use in generally the same sort of form, was invented by Daniel Fahrenheit at the beginning of the 1700s. He had a long tube and he put alcohol in it, and he invented a scale so it's easy for people to understand how hot it is or how cold it is. It's called the Fahrenheit scale, and we use this in imperial measurement. And according to his scale, the freezing and melting of water occurs at 32 degrees Fahrenheit. The boiling of water occurs at 212 degrees Fahrenheit, and the average temperature of the human body is 98.6. Now, this scale is a little unwieldy, which means a little bit difficult to use because the numbers aren't even. So a man a few years later named Aldous Celsius invented a simpler scale. And this is the one we use in the metric system, and everything's in multiples of 10. It's very easy to use this scale. 0 is freezing of water, 100 is boiling of water, and the average human temperature is 37 degrees. About 5 years after Mr. Fahrenheit invented the thermometer, he decided to put one, to make one that had mercury in it instead of alcohol. Mercury is the only metal that's liquid at room temperature, and it's very, very sensitive to temperature changes. And so it was an excellent medium to put into the thermometers, and we used them well into the end of the 20th century, except one little problem. The tube is glass and mercury is very poisonous. So when people would break a thermometer, the mercury would get out. So now we are going back to his original substance, alcohol, inside the thermometers. So this one measures room temperature. It doesn't have a real wide range, but it's what we need in our classroom to know if it's too hot or too cold. Now, before we had thermometers, we had something called a thermoscope. This was invented by Galileo. It was invented very close to 1600 and about 1593. It's a long column of water inside a closed glass tube, and it's got all these little glass bubbles full of liquid. At the bottom of each one of the glass bubbles is a tag with the temperature. It doesn't have a wide range at all. It's very short, from about 68 degrees to about 84, 86, something like that. But it's good to check the temperature in a room. So what you do is you don't look at the bubbles at the bottom, you look at the bubbles at the top, and you look at the very last tag that's hanging there. This one says 76, so my classroom is 76 degrees. This is called a thermoscope. Thermo means heat and scope means to see. So I can look at that and see that the temperature is 76 degrees Fahrenheit. We've got all different kinds of other kinds of thermometers because so much of what we do and what we deal with is temperature sensitive. For example, I bet you've had your temperature taken quite a bit since the middle of March. So this is a thermometer that we use to take the temperature of people. The average human temperature is about 98.6. Dogs and cats have higher temperatures than we do. Theirs are around 100 to about 101.5. Chickens have an even hotter temperature because they're birds. They have a higher rate of metabolism, and they've got their average temperature is about 104 to 105, depending on the breed of the chicken. So we know that inside our bodies, we're certain temperatures. I'm going to show you a little animal that's very different from that. This is a gecko. His name is Peanut. Say hi, Peanut. Peanut is a gecko. He is a reptile. He's cold-blooded. He's dependent on the air or the water around him to help control his temperature. So that's why when you have a gecko or a snake or a turtle in their terrarium, you need to have a spot with a light or with a hot rock so that he can sit on it and warm his body. He cannot achieve a stable temperature on his own. His brain isn't sophisticated to do that. Warm-blooded animals can control their internal temperature, like mammals and birds. So we'll put him down. Now, let's look at a couple of other thermometers real quick. This is a soil thermometer. This helps us determine when it's warm enough to plant our seeds. This is a composting thermometer. You see that green part? That's the part where you want the needle to be in that green part so that you'll know how warm your compost heap is. If it's less than 80 degrees, it won't decompose. If it's over 160 degrees, it's too hot and it kills the microorganisms. So you need it right in that middle range. We have an oven thermometer. This helps us judge how hot our oven is running. We also have, let's see, I've got a couple more. We do a lot of pond ecology here at the Environmental Center, and we take the temperature of the pond water. This is the thermometer we use. It's in a plastic case that keeps it from breaking. We tie a string, a long string, and throw it out in the water, and then we can read the temperature of the lake. Okay, finally, I want you to think about the hottest thing you can think of. Here on Earth, that might be something like a volcano. The lava, the melted rock that comes out the top of the volcano is about 2,140 degrees. The magma deep inside the earth, before it comes out, it's still inside the earth, we call it magma, and it's got a temperature of about 2,400 degrees. So both of those are really, really hot. But the thing in our solar system that's the very hottest is going to be the sun. The sun is a star. It's extremely hot, especially in the very, very middle where there's a lot of nuclear fusion going on. It's about 27 million degrees Fahrenheit. So the center of the sun is extraordinarily hot. The outside of the sun, it ranges from the photosphere being 10,000 degrees to the chromosphere being 7,800. So we measure things, measure their temperature, how hot or how cold they are, using thermometers. And I'm going to turn this back over to Mr. Broughton in case you have any other questions about temperature. Thanks so much. I hope you have a delightful day.
Thank you, Mrs. Fuller. One question came in, which is, how do we know that the temperature, like at the center of the Earth, is what it is? And scientists know that because they send seismic waves down through the Earth's surface, because you can't dig down there. That would be much too difficult. But they send waves down into the Earth's surface, and those waves hit things like rock or iron and solid iron or melted iron, and they bounce back, and that tells them what is down there. And then to find out the temperature, they know the center of the Earth is liquid iron, and they melt iron in a lab and see what temperature it melts at, and then they know what the temperature is inside Earth's surface. So that's how they figure that out, kind of basically. So we are going to move on to solids, liquids, and gases with Miss Nash.
Hello, third grade. Welcome to my classroom. And we're going to be talking about solids, liquids, and gases, the three states of matter, the form in which stuff exists. So those are solid, liquid, gas, and let's define them. A solid has a definite shape and a definite volume, like my rock. A liquid has a definite volume, but a shape that can change. And a gas takes the shape and space, the volume of its container. So I blew up this balloon with air. The air is a mixture of different gases, and that mixture of gases took up the space of the balloon and it filled it. There's only one substance that's found in all three states naturally on our planet, and that would be water. So I have a bowl here, and I have a piece of ice that's melting, and as it warms up, it's going to become water. And then that water can become a gas. If I leave the bowl out for a week or so, maybe the water will be all gone. What happened? It evaporated. So that word evaporation contains a clue. That word vapor, meaning a gas. And the bowl also shows us that that vapor can be turned back into liquid. So on the outside of my bowl, it's very wet. And the bowl's not leaking water, it's condensing it from the air that's around in the classroom. It has a lot of water vapor in it, and it's condensation. So the change in temperature means the state of matter can change. And why does that happen? So the water, the ice, the liquid, the air is all water, H2O. Why is it so different? And the reason is that at the particle level, it's changing. So take your fingers like this, and let's imagine that these are a solid. And a solid is all stiff. There it is, doesn't move. But then if I add some heat and melt it, the particles get loose, and they start moving around as a liquid. If I heat them up, then they're going to become vapor, and they're going to go, pow, let me out of here. And they're going to expand all the ways. So what's changing is the kind of the arrangement and behavior of those particles. Now, liquid takes the shape of the container. I've got a beaker here, 4 beakers, all with the same amount of water, 200 milliliters. And I've got some different containers. So let's see that the same volume can take many shapes. There we go. I've got a big bowl here and pour it in flat. I've got a tall beaker here. Let's see. And sure enough, it's the same. So all these different shapes of liquid have the same volume, but a different shape. Now gases are just weird because we can't see them usually. And they're just kind of everywhere. How do we even know they're there? Well, I have a beaker here, and it was full of air, and I put a balloon on top. And I thought, I'm going to get that balloon down inside. I push it down in with my finger, and now I blow it in. No matter how hard I blow, it won't work. Because the air inside, those molecules of gas, are pushing it back out. They say, no, we're here now. Get out of here. We can't come in. So I took another beaker, another balloon, but before I put the balloon on, I put some steel wool. Remember that word steel? So that steel had iron in it. And then I put the steel wool inside and added some water. And that steel wool began to rust. You leave a nail or a hammer outside for a long time, it's going to rust. What's happening? So then I put a balloon on top. And lo and behold, overnight, my balloon went down inside the beaker. How'd that happen? So all those oxygen, so what happened with the rusting? Now it's iron oxide. Here's that word oxide in there, oxidation. The oxygen molecules in the air are no longer a gas, now they're a solid. So they're taking up a lot less space. And as a result, the balloon got pulled down inside. And we can see those 3 states all around us in our house. I have my bottle of Topo Chico here, and it's got solid, got liquid, it's got gas inside. You may not be able to see it. I shake it up. Oh, then you can see some bubbles in there. Carbon dioxide gas that was in there under pressure. That's why when you pop it, you go, it's the pressure of the gas says, let me out of here. Now, if I take my Topo Chico, you can see some little bubbles coming up in there, maybe. If I leave it overnight, I forget it. I go back the next day to drink it, and I'm going to go, it doesn't taste right. You leave a Coke out overnight, and you go back, and it's not going to taste right. What happened? The gas saw its opportunity to escape. It went out into the air, floating around in the air. So gases are going to try to escape. Get out of here. Another example of those three states in a snack form is popcorn. So if I have my popcorn, it's really hard, seems solid to me, but popcorn came from a plant. And plants, like all living things, have a lot of water in them, even though we can't really see it. When I put my popcorn in the pan, what happened? It popped. Why did it do that? Kind of like the Incredible Hulk. Inside that popcorn was some water. And as it got hotter, remember that's how it changes state. As it got hotter, it had to get out, exploded, and that's how we get popcorn. We can also think about gases. We use gas to pump up our bicycle tire, keep the tires in our car inflated, and that gas is under pressure. Now, here's my challenge for you. I want you to find 3 examples of all 3 states of matter around your house and see if you can think about how the different kinds of matter in different states are useful to us. And here's another challenge. I can pour a liquid and it takes up the shape of the container. This is sugar. This sugar, I can pour it, it takes up the shape of the container. Does that mean it's a liquid? I wonder. What do you think? How could you investigate? You could use your fingers. Your fingers are totally sensitive. You might feel it and see. You might use a hand lens and look at it and see what you can discover. Is it a solid or is it a liquid? And that's all I have. I'll turn it over to Mr. Broughton for a question.
All right, thank you, Ms. Nash. And we did have one question, which is, how can a liquid become a gas or a solid? So to kind of explain that, I'm going to share my screen with you, and I think I've got a little graphic organizer that will help answer that. So there we go. If a liquid can become a gas by adding heat. So if you add heat to a liquid, it will evaporate and turn into a gas. A liquid can become a solid by taking away heat. If you allow liquid to cool down, it will freeze and become a solid. So if you put it all together and just start with solid, if you add heat to a solid, it will melt and become a liquid. If you add some more heat, that liquid will evaporate and become a gas. And then if you take away heat, like cool that gas down, it will condense and turn back into a liquid. And if you keep taking away heat and cool that liquid down, it will eventually freeze and become a solid. So that is how a liquid can, or any substance, solids, liquid, or gas, can change from one to another. It all has to do with adding or taking away heat. All right, we're going to move on to our next teacher, Mr. Ramirez, who's going to talk about sinking and floating.
Hello, 3rd grade. My name is Ms. Ramirez, and in this segment, we're going to be learning about the properties of matter of mass and sinking or floating. So to start off with, mass just tells us the amount of matter that is inside an object. And usually, or probably in previous grades, you probably compared masses of objects using a simple tool called a pan balance. So we're going to compare the masses of these two objects. We have a little bead and a candle. Go ahead and make a prediction. Which one do you think has more mass and why? We're going to go ahead and put them inside our balance, and we're going to see what happens. So our bead's going to go in first, and our candle's going to go in next. So what did you guys notice? So I noticed that the candle side went down. So the way the pan balance works, the side that is heavier is going to be on the down side. The side that is lighter is going to be on the upside. Now remember this information for later because we're actually going to test these objects to see whether they sink or float. So remember these results. Another way that you can measure mass of an object is by using another type of balance called a triple beam balance. So let me see if I can slide this over. This is a triple beam balance, and it gives us an exact measurement of mass in terms of grams. So here we have a box of iron pyrite. Iron pyrite's not real gold, it's called fool's gold, but it sure is pretty. We're gonna see if we can measure the mass of this box of iron pyrite. The way the triple beam balance works, there are 3 scales, and you're just gonna have to experiment with moving these scales back and forth. And your goal is, there's a 0 right here, your goal is to move these scales back and forth until that white line is in line with this 0. So you always start with the biggest weight first, then you move on to the second biggest, and then this front weight right here, the smallest, that will be the last one that you move. Now, once you have it to where it is equal to the 0, you're gonna read the measurement. And to read the measurement, I have a close-up of what it could look like. So these are our 3 scales. You're gonna read the middle scale first because it's the biggest. Then you're gonna read the 10 scale next, the one at the very end. And then you're gonna go to the front and read the 1 section. So for example, we read this one first since it's the biggest. It's at 500 grams. Then we're gonna go to the back and read the 10s, and this one is at 20. So we have 500, 20. Now let's read the 1s, and it's at 3.2. So you put all those numbers together and you get 523.2 grams. Now, the reason that we had to learn about mass was because mass plays a role in whether an object will sink or float. So when we combine concepts of mass and volume, we get what's called density. And density is simply an object's mass per unit volume. Now, I know that's a lot of vocabulary words to remember, so just to give you a visual of what all these words mean, we have our 2 boxes of iron pyrite. Go ahead and make some comparisons between these two. Compare their mass, their volume, and their density. So I can tell by holding them that this box has more mass. It feels heavier. I can also see by looking at them that this box is more dense. It has more matter inside of it. The volume is actually the same for these. They take up the same amount of space. And to find the volume of a box, the mathematical way is just to multiply the length times the width times the height. So that's a comparison of the mass, volume, and density of these 2 boxes. Now we're actually going to see whether objects will sink or float. And an object's ability to sink or float, again, depends on its density. So we're going to compare these objects. So as I show them to you, make a prediction on which ones will sink and which ones will float and why. So we have an empty Coke can. We have a pumice stone. We have a piece of wood. We have a ping pong ball, a limestone rock, a wax candle, and our bead. So just to review, really quickly put them in order. Which ones do you think will float? Which ones do you think will sink, and why? And we're going to move to our back table so that we can test it out. So the tool that we're going to be using to test sink or float is just a container filled with water. So here we have it. We're going to start off with our 2 biggest items first. So we have our can of Coke. We have our piece of wood. And These are actually two very common items that we find, unfortunately, out in our lake across the street. So litter is a big problem in our ponds and lakes. We also have a pumice stone that's going in. We have our ping pong ball, our wax candle, our limestone, and our little bead. So hopefully you guys were able to see some of those observations. The objects that were able to float are the objects that are at the surface of the water. So the objects that floated were the empty can, the piece of wood, the pumice stone, the ping pong ball, and the wax candle. So did any of those things surprise you as to why they floated? So I saw that some of our biggest things actually floated while some of our smallest things actually sank. So why do you think that is? So the objects that float, we say that they are less dense than the liquid they are in. So in this case, these items that floated are less dense than the water. The objects that sank, that fell to the bottom, were the bead and the limestone. Because they sank, they are more dense than water. So again, just because something is big doesn't mean that it's going to sink. And if you remember our experiment with the wax candle and the bead, the wax candle had more mass, but yet when we tested its ability to sink or float, it actually floated while our lighter bead sank. So mass by itself is not going to tell us whether something is going to sink or float. Again, the ability to sink or float depends on density, which takes into consideration an object's mass and volume. So we can't always tell just by looking at something. So to review, we learned that mass is the amount of matter that is inside an object. And we can measure mass using a simple pan balance or a triple beam balance. We also learned that density affects an object's ability to sink or float. And density is the amount of matter or mass that is in a certain volume of a substance. So if we look at our picture here, the boat and the bottle are floating, so they are less dense than the water. The tire and the rock sank, so they are more dense than the water. So I have an at-home challenge for you guys. We're going to see if you can create a boat that can carry at least 5 pennies and that will float in a tub or a sink. I also want you guys to think about this reflection question. How have you observed the concept of density either at home or outside? And how do you think it relates to you, or why is it important to learn about density? And that is all I have for you guys today about the properties of matter pertaining to mass and density. We're going to give it back to Mr. Broughton, and he's going to answer any questions that you might have.
All right, thank you, Mr. Ramirez. And we did have one question, which is the aluminum can floated in water. Would an aluminum cube float in water? And I don't really want to answer that because of the challenge that Mr. Ramirez gave you, because if you make a boat, a great material to use to make your boat would be aluminum foil, which you probably have at home. And you'll be able to experiment with aluminum on your own at home, and I don't want to tell you any answers that might affect how you build your boat. So let's review what we did today. I'm going to share my screen real quick. And go back to this slide. So you discovered that matter has measurable physical properties, and those properties determine how matter is classified, changed, and used. So you learned how to measure the temperature of matter, how to classify matter as being a solid, liquid, or gas, how to test if matter sinks or floats in water. And then remember, if it floats, that means it's less dense than the water. If it sinks, that means it's more dense than the water. And you learn how to test to see if matter is attracted to a magnet or not. And the tools you use to do those things are a thermometer, a beaker, a pan balance or triple beam balance, and a magnet. So thank you so much for joining us this morning. We'd like to know how we did today, so you can let us know by going to www.tiny.cc/EEC feedback. and telling us about what you thought about today's field trip. We look forward to seeing you again. We're going to do another third grade field trip in about 3 weeks, so go ahead and register for that one, and we will see you again. Have a good rest of your day. Bye-bye.